3, 2, 1. Well, good morning. A question. As usual, some words are more important than others. If you read this text, there is one single word which gives away the answer immediately. If you find that word, that's it. Problem solved. And what is that word? Could you tell me, please? One word which immediately gives away the answer. What word is that? Diverging. Can a diverging device form, create, generate, produce a real image? No, that's it. It just can't. So nothing else important for this question. Thinking, again, is not involved at all. Just simple knowledge. Diverging devices cannot form real images. Well, now we have to follow the strategy to calculate whatever we need to calculate. Lens, not a mirror. So we need to remember different symbols for different types of the devices. Concave mirror, convex mirror, assuming that an object is always on the left. A converging lens, a diverging lens. Those symbols represent actual shapes, but we shouldn't draw actual shapes. They would confuse us. Plus, when we talk about lenses, we make an assumption that it's a glass in air or something like that. Now, actually, sometimes we don't have to draw a diagram. We can just write an equation, number one. Why not? And equation number two. And now we can write these equations using numbers. For example, magnification equals over 15. We don't know this. What else? Oh, no, actually. Yeah, we don't know that. And we don't know this, but the distance, 60 centimeters in front of, let's keep centimeters. And now, well, another equation. Okay. Oh, 60. You didn't give me a chance to walk. Okay, what do you want to say? Yeah, I have to go back and fix it. It's a diverging device. For a diverging device, the focal distance has to be negative. That's why this word is is used magnitude. So the magnitude of the focal distance is indeed 30 centimeters because it's magnitude. However, we need to know that for conversion devices, the focal distance is positive. For divergent devices, the focal distance is negative. But that's an easy fix. So again, we just need to know the difference between the magnitude and actual value. Magnitude is never negative, and actual value, well, depends. All right. Well, we can solve it, right? The image distance has to be negative because for a virtual object it's always negative. Negative 130 minus 1 over 60, which is 2 times 30. So 60 is a common factor, 2, 3, 60. Now we have to flip it. 60 over 3, 20. So if we take a ruler and we measure a distance from a lens to a location of a virtual image, the number should be 20. Yeah. But because it's a virtual, we have to assign a negative number to that. Quantity we also call distance, but it's not just distance, it's an image distance, so slightly different term. Now, where is the image? Yes. So these are rules which we can remember, but of course a good diagram would show it, and we will draw a diagram, but also it's handy, it saves time just to know when a mirror is involved, a mirror doesn't transmit light, so virtual images will be behind the mirror on the right side, but real images for a mirror are supposed to be on the left side with the object. But a lens is a transparent object, transparent device. So to form a real image, light must get through, will be on the opposite side. Virtual image is supposed to be formed by a lens, supposed to be formed on the same side with the object. So focal distance 30. Well, we need only the right one, but still we need the left one to know where we place, where we should place. Oh, this is diverging, so 60 is here, 60 is 2 times 30, 60. We place an object here, an object, and now we can draw 2 rays. Now we need to know which focal point to choose to draw a ray correctly. This is a diversion. So what does it do? Well, a conversion device always bends a ray toward the principal axis. A divergent device always bends a ray away from the principal axis. So in that case, we have to use extensions first, and then we can draw an actual ray. Its extension should travel through the focal point. And now we can draw a second ray. Oops. The second should go through the middle point, through the center. What does a ruler do? Rulers rule. They rule the light rays. So this is 20 centimeters, as it has been found, less than 30, less than 60. That's it. And the second equation hasn't been used yet, but we could use it to calculate the height. It should be equal to, well, a minus comes from the equation. A second minus comes from the image distance, which is negative, divided by 60 times 15. And what does it tell us? Negative, negative makes it positive, 0, 0 cancels. 2 times 15 is 30, 30 over 6, 5. I think we have found everything. Magnification is actually 1/3, 5 over 15. So even if we call it a magnification, it doesn't always tell us that the image is larger. It's just a term, a name. All right, so question. So here I have a setup similar to the one you've used or will use in a lab. It's basically a source, a lens, a screen. That's it, nothing else. I planned to use it yesterday, didn't have time for that. This is the source. Not this is, no. This is the source. A bulb with a long vertical filament. But I don't want to light shine in all directions, so I use a screen. And now on this foggy screen you can see a light, but that's not an image, not a focused image. So what do? Well, we can move any of these objects. Yeah? There is a specific location for this lens when we see a sharp, enlarged image, and there has to be a second location when we see a sharp, reduced image. Of course, we can calculate the distances because that's just the image distance. And of course, there has to be symmetry right now. This distance is equal to the distance which the lens was away from the source when the image was sharp. Well, but the question is not about this. The question is what's going to happen if right now I'm going to cover the top part of the object. Well, the source. This is the bulb, which is a source, an object. I can take a piece of paper. I can just cover the whole thing. No light travels through the lens. Well, I can cover the lens. Yeah. But the question, what's going to happen if I'm starting moving this page slowly down and the top part is being covered? What should happen? Well, you have answered, and now you can check your answer. You can see what's happening. The top part of the image remains bright, but the bottom disappears. Why? Well, because as we know, the image is inverted. That's it. What's going to happen if I cover the, let's say, top part of the lens? doesn't affect the size of an image, it just gets dimmer, because still, even a small part of the lens transmit light from all points of the object, but less. Well, you have played or will play with this setup in the lab. In a lab, you have an extra object. You can also see what's happening if you start covering the left part of an object. In that case, because the image is inverted, the right part of the image disappears. And, well, quickly, very quickly, that's a conversion lens. And we have a focal distance, and let's say we have first an object placed far away. So what do we do? First ray, same focal distance. If a ruler rules, and I rule a ruler, who am I? That's going to be an image. So if I start cutting out, covering this part, so these rays cannot reach the screen. There is a screen right here. We need the screen to look at the screen to see that image. That's it. Well, in our example, we didn't change the distance from the screen to the source. Yeah? This distance, which is actually the object distance plus the image distance, was fixed by the setup. We've been moving the lens back and forth. That's what we did. And of course, we can write an equation. And now we can set this distance to a fixed value. So basically now we have two equations, and if we solve them, we can calculate two answers. One, which represents the location of the lens, which forms enlarged image, and second, on the screen, the location of the lens when a smaller reduced image is formed wide. Two solutions, because actually, if you combine these equations, you get a quadratic equation because of the fractions. For example, what could you do? Di equals this, and the length might be 80 centimeters, and a focal distance maybe have to figure out the focal distance. How do I do that? Well, this light is very far away, so light traveling from this light practically parallel to, well, each other. And now all I have to do is just find the distance where this lens makes a sharp image on the bench. It's like the sun, the looking glass, and a tiny ant you hate. I don't hate. You, no? And this will be the focal distance. The image distance is infinity. So let's say 20 centimeters. And this is a minus. Now we can take this expression, plug it in this equation. 1 over 20 should be equal to 1 over 80 minus object distance plus 1 over object distance. And now, when you solve it, you get a quadratic equation, which gives you 2 answers. And by the way, since I said it, measuring the focal distance of a conversion lens, that's what was happening. We have a lens, very far away we have a source, so light travels through the lens and gets focused on a surface. So the object distance is practically infinitely larger, and if you write an equation, when we're dividing by a huge number, the result is practically 0. So this distance is the focal distance. We just need to make sure the source is very far away. That's it. Well, so we have answered the question. Now, just a reminder about terminology. Nothing very technical, but when we say convex lens, we mean made of glass placed in air, which makes it converging. When we say concave lens, it means made of glass placed in air that makes it diverging. And when we say thin lens, it means we don't talk about any other lenses. Of course, if we would make a thick lens, we just couldn't use any of those equations, because for the thick lens, there is no focal point. A thick lens is like 2 large prisms. The rays would cross over a large area, and we just couldn't use any of those equations. So for us, in this class, any lens is a thin lens. That's it. And again, a review. These are only questions, situations which related to any possible questions. Nothing else can happen. And the optical devices, well, as you know, people have been using them for centuries, even thousands of years. Looking glass. This is a looking glass. Yeah. What is an optical device like this? It's a combination of 2. So you can look through, adjust the sharpness of an image. How does any optical device work? Well, the idea is very simple. A first device forms an image of an actual object, but that image becomes an object for the next, and then for the next. And if we need, and we don't, but if we need, we can always just apply those equations several times in a row. First, for the first device, which forms the first image, that image becomes an object for the next, well, lens or mirror, and that image might become an object for the next, etc., etc. That's how it works, basically. Our eye is an optical device. And when we talk about vision, we always involve 2 devices, at least. Even if we use a looking glass, that's the first lens, and that's the second. So this device makes an image of an object which might be actually virtual, but our lens treats that image as an object and makes an image of that image on the retina. That's how a normal eye operates. And a normal eye for a healthy person can focus on very large distances from about 25 centimeters to technically infinity. However, if that's not the case, we have to correct the vision. For example, myopia happens when the lens cannot focus an image of a faraway object on the retina. What do we have to do? Well, the idea is simple. If the sharp image is formed slightly in front of, we just have to diverge the rays a little bit. That's why we use divergent lenses. So this is a system. Ideally, there should be no spacing. That's why people use contacts, but I don't recommend using contacts. They don't make you look smart. So if you use contacts, the actual optical power will be equal to just the sum of optical power of that lens plus the optical power of an eye. And if we use, well, if we need to correct the opposite, the farsightedness, what does it mean? It means when the object is close, the lens cannot focus sharp image on the retina. It's beyond it. So what do we have to do? We have to converge those rays. That's why we use a conversion lens. That's it. So the idea is simple. Technicalities, of course, are different thing. Well, another phenomenon we're aware of, colors. Yeah? We can see the rainbow, and there is a phenomenon responsible for that. Turns out that the index of refraction depends on the color, slightly, but does. So when white light travels through a prism, red, yellow, green, blue light bends slightly differently. The phenomenon studied by Newton as well. And we don't need this mathematics, but the physics is actually really interesting because it turns out light of a different color interacts with the matter differently. The blue interacts stronger. Because of that, it slows down more and it travels slower. That's it. Then the red one. A little bit, but still enough to make a difference. So all we need is a prism, just a slit, and so now the light travels like this. If I use the prism, I want to bend it on the screen, and we know air glass situation, light bends toward the base of the prism. So if I want to bend it like this, the base should be like this. Let's see. Where is it? One surface is foggy, two transparent, so it should go through transparent surfaces like this. Where is it? Has to be somewhere. Oh, it's on the wall. Here. Here is the rainbow. We can see that light, well, the red color is on the left and the greenish on the right, and then going to be blue. So light travels like this, and the red bends less, the blue bends more. This, what we call normal dispersion. In certain circumstances, in gases, the anomalous behavior might exist, but for the normal dispersion, that's always the case. And the rainbow actually is a very complicated physical phenomenon. It involves several optical laws. First of all, refraction happens. When billions of water droplets float, white light travels through, refracts, then due to total internal reflection, reflects, and then due to dispersion, makes a spectrum, which we wouldn't see if we didn't have a lens in our eye. So rather complicated physics behind this simple phenomenon. Now, we also said that depending on the situation, to describe what's happening, we may think of light as of a wave traveling away from a source. Some things, some phenomena cannot be explained by the particle view. So we know that. And the wave optics based on, well, these statements, we treat light like wave, and everything we know about any wave can be applied. It has period, it has wavelength, frequency, speed. The relationship between speed, frequency, and wavelength is the same as for any other wave. And this equation can be used for light in vacuum, air, water, in any medium. But all three variables are supposed to be related to the same medium. We also said we know that the frequency is a function of a source. The source makes the wave, and then the wave travels away. And when wave travels through different media, frequency can't change, but speed can. And if speed changes for light, it slows down. That affects the wavelength. Wavelength also changes, shrinks. And the visible spectrum is described by a very narrow span of wavelength from 450 nanometers to about 700 nanometers. We cannot see beyond that spectrum. And the wave theory of light actually tells us how to calculate the angle of refraction. We don't have to do this mathematics, it's just an example, but there's a nice app which demonstrates what's happening. It's based on the so-called Huygens-Fresnel principle. A wave front is approaching the boundary, and each point of this boundary starts acting like an individual source. And now all waves start traveling from each point in both media, but with different speed, faster or slower. And more importantly, they interfere, and as the result of that interference, a new front is formed, and we can see the angle of reflection is equal to the angle of incidence, but the angle of refraction is related. How? And here, well, if you want to, you don't have to, but if you want to, you can just do this simple mathematics. And the Snell's law automatically is derived from this, plus automatically index of refraction is defined as the ratio speed of light in vacuum over speed of light in that medium. Done. Pretty neat. What else do we know about waves? They interfere. Remember, if we have two sources, we can generate a standing wave under certain circumstances if we fiddle with speed, frequency, distance. And we know that the standing wave has certain locations where we observe maximum of intensity and certain locations where we observe nothing. We call them minima. So what's going to happen if we try to generate a standing wave in space, not just between the sources, but everywhere? Well, there are several models which help us to figure out what might happen. First, we know from each source, wave should travel equally in all directions. So one wave comes from source on the left, second wave from the source on the right. And then when two waves interfere, overlap, superposed, when a crest and a trough, a crest from one wave and a trough from another wave meet at the same place, they cancel each other out. A completely destructive interference happens. No intensity at all. A minimum is reached. But if it's a crest and a trough, they amplify each other, and we should observe maximum intensity. Well, again, we can look at an application first. So this is done. This is a time-dependent picture of a steady wave in a space around two sources. We can look at single point here, for example, and we can see it's always black, which means two waves here always cancel each other. And we can see that there's a different point where it's black and white. That means oscillations is happening. But it's hard to tell if it's happening with maximum or minimum or something else. So there's another application, color-coded. So for example, if we look at this yellow spot, what does red, black, and blue represent? Red represents the crest of a wave, blue represents the trough, black, the equilibrium. So at this point, they change. So at that point, we observe oscillation in intensity with maximum possible amplitude. Here, if that would have been a sound wave, and it will be, we would observe the maximum of intensity of the sound, which we call loudness. All we need is a source on the right, a source on the left, a function generator, an ability to untangle wires, very important. All right, let's span them away. Now I want to make a wavelength about this long. So if the speed of light is about 315 today, so I have to tune up the frequency to that number, 250, 335, 320. So right now the wavelength should be about 1 meter, which means it should have 4 quarters, 25 centimeters each. And a quarter is a distance from a maximum to minimum. So if you move left or right about 25 centimeters or more, you should observe the change in the loudness. Slightly, but should. Also, because the motion is relative, that's not 25 centimeters, that's just 5 and 5. This is 25. I can do it for you. I can move slowly. Because now relative to you, again, distance changes. And even I, standing nearby, can hear how loudness changes. It doesn't go to 0, of course, because a lot of extra reflection happening in this room This room should have been absolutely empty. We could use a sound meter measuring decibels, and we would observe a standing wave. There's another model for that, optical model. And models are very important. First, we have to remove the slit. Now, this dot represents one source, and these are wave fronts traveling away. That's a second source. And if we place them together, we can see overlapping. That is interference. So at certain points, wave should completely cancel each other. At certain points, wave should amplify each other. And this is what you can do at home. Just have a pen with water. When the thickness slightly changes, so it affects how light travels. And this is one source. One wave travels away. Two. Now, interference. The most important difference between the sound wave and light wave is the wavelength. You know, this sound wave wavelength is about 1 meter, but for light it's nanometers. So even if light travels like 1 centimeter, that's a huge distance for light. That makes physics kind of easier, actually. The problem is we cannot see those waves. We could hear, if we walk around, we could hear how loudness of the sound changes. But for light, that's not the case. So for light, we have to place a screen and look at the screen. And on the screen, we would have to see bright spots when maximum is occurred, or nothing, dark, where there is no light at all, where minimum is occurred. And I'm going to go back to that picture in a moment. So one more. This is a very nice. Oops, wrong. Not this one, this one. A representation similar to my experiment with water. Yeah. The problem with light that even two laser pointers manufactured right after another will have slightly different wavelengths. We easily can manage the same frequency for two speakers, but we can't manage the same frequency for any two actual light sources. So in order to have two identical light sources, we actually use this. We use one source, and then we split it in two. In that case, these two sources, actual slits in the screen, form the interference pattern. But in order to see if it's not a light, we have to place a screen and look at the screen. That's how it works. And with that, what we would see for a monochromatic green light, so we have a screen, and on the screen, if we use green laser pointer split in two, we would see green fringes or spots, then nothing, black, green, black. So each bright spot we call a maximum because it represents where the maximum intensity of light is reached. No light, we call a minimum. And I just said we cannot use two light sources. So that's why we use one source and split it. This experiment has been proposed and actually done in 1801. And Thomas Young wasn't even a physicist, he was a physician. That was a hobby for him. He wrote a paper, and for almost 20 years, no one paid attention to that. What a physician can write about physics. So, this is a geometrical description of this phenomenon. As we said again, two sources. Well, we say sources, but we mean two tiny scratches, slits. They should be very close to each other. They should be, the distance between those sources should be close to wavelength of light, micrometers, fraction of a millimeter. So, of course, this is a huge exaggeration. In reality, we could not see the difference between this and this. But they split. There is a distance between those sources. And light travels away, interferes. On the screen, we see maxima. How do we call them? The one in the middle we call central. And then to the right and to the left, to the central maximum, we observe the first and the second. But there is no such thing as central minimum. This place is taken by the bright spot. So there is no maximum, there is no minimum number 0. To count minima, we have to start from number 1. So that's why we count maxima and minima differently. To count the maximum, we start from 0, then first, second, third, fourth. They end at a certain point. And to count minima, we have to start from 1, 1, 2, 3. And the expression which tells us at which angle should we look from the location of the device to see a maximum or a minimum is given by these two equations. On the top, that's the condition for constructive interference for the maximum. Again, D represents the distance between two sources or slits, tiny number. And M represents that counting number, 0, 1, 2 for a maximum, or 1, 2, 3 for the minimum. And theta is the angle we should measure with a protractor to observe the mth maximum or the mth minimum. That's it. Well, one more about counting, how we call them. This is how we count maxima. This is how we count minima. Now, slight difference between the theory and practice. Again, in practice, we cannot ever have two identical light sources. That would give us very bright, equally bright pattern on the screen. In reality, we use one source, split the light, so the pattern actually dims away, dies out very quickly from the central region of it. You will be doing a lab where you will be using a special sensor, light sensor, to measure intensity of light. So you will just move that sensor left, right, and that will tell you the intensity in a number. If you would be using two ideal sources, that would have been the pattern. So you move it in space, intensity changes, maximum, minimum, maximum, minimum. In reality, the pattern will look like this. Close to the middle, intensity changes, but then it dies out, which is fine. All you need is a couple of peaks, couple of maxima. Question. So, two sources generate a standing wave. We place a screen. We look at the screen and we see this pattern. What's going to happen to the fringes? bright or dark spots, lines, if we would move screen away, farther away. And these are only possible options. Nothing. We say the pattern shrinks, or the pattern expands. If the pattern expands, these lines move away from each other, farther apart. And of course, the answer is in the picture. It's not in well, equation also works, but basically we need to understand what is happening. So again, first of all, the source number 1 and the source number 2 cannot be differentiated by an eye. So it's here, that's it. There's a screen right here, and light travels only along certain paths, right to the middle, the central maximum. Then light travels to a different spot. This is what we call theta 1, maximum number 1. Of course, symmetry says there's a maximum on the left. And of course, this is theta 2. All those angles are measured from the middle line, which is perpendicular to the screen, m equals 2. And on another side, well, m equals 2, theta 2. And what's going to happen to these bright spots if the screen is being moved out away, farther away from the source? Well, you just have to redraw the picture and extend the rays. Now they go further, right? So what's happening to the distance? Increases. So the pattern expands. If we would move the screen closer, the pattern would shrink. But of course, the equation should tell us the same. For example, we can take any angle, theta number m, for the mth maximum. What do we change in this equation? Do we change m? No, we're just looking at maximum number 2, for example. Do we change the wavelength? No. Do we change d, distance between two slits? No. What does it tell us? This equation is useless. But why? Because it doesn't involve a variable which changes. What does change? The length, L, distance from the source to the screen changes. So we have to write an equation which has that variable in it. And that equation, of course, is related to, let's say, this is the distance from the central maximum to the maximum number 2. Normally we call it L2, L1, L3, or in general, L number m, from the mth maximum to the central maximum. And where else now we can see this angle, theta? Well, the theta 2. In general, we always have a right triangle distance from a source to the screen, distance from a central maximum to the mth maximum, and this angle. And tangent. When we move a screen in any direction, we do not affect these angles, they stay the same, but we affect this length. So when we move it away, length increases, the distance between the fringes increases. And this is another equation which we may need to use sometimes to solve a problem, and we will. So that's the answer. Further report. Question. To this question, you need, well, there are so many conditions. You need a calculator, at least one hand, at least one eye, an ability to press buttons, know the difference between degrees and radians, use that knowledge of the difference between degrees and radians. The wrong answer to this question might affect your final grade. Or not. But you don't know. So you have to apply your best effort. Well, there is a problem I don't know how to solve, and that problem is I have no idea how to convert my calculator from degrees to radius. But that's not going to stop me. I know that 1 radian is about 57 degrees. So, degrees, you know what? The better conversion factor, which always on the first page of the equation sheet, is pi radians, the same as 180 degrees. So if I need 0.1 over radian, and I need to convert it in degrees, all I gotta do is this pi over 0.1 should be equal to 180 over a question mark, and my question mark should be equal to 180 times 0.1 over pi. That's sufficient already. So let's see. No, I don't need second function. Sine. I know that 180 times 0.1 is 18, but I'm going to do the whole thing. 180 times 0.1 divided by, on my calculator, pi is here, second function, 3 equals so my calculation tells me the sine of 0.1 is equal to 0.099. Bless you. So I'm going to switch first to the slide. 0.099. Is it almost what? Let's see what's. This is equation number 5. Oops. Well, 2 is the correct answer, so the majority is right. Yeah. 0.099 is about 0.1. What does it tell us? It tells us this. That's a very important time-saving knowledge. For small angles are angles up to 10 degrees could be considered small angles, or about 0.2 radians. For small angles, we actually can just drop these symbols. We don't need SIN, we don't need TAN, but only if the angle is measured in radians. That doesn't work for angles in degrees, no. But if we have a small angle and we measure that angle in radians, that's it. We can just scratch off those symbols, sine, tangent, and use just angle. And that helps for solving problems, because when we have to combine sine and tangent, that's a complicated situation. But now, with this knowledge, if we go back to this problem, we actually can write that this ratio, theta over theta, this angle, theta m, should be equal to this. And also, we can get rid of the tangent symbol. And these equations much easier to be solved. Plus, we can immediately relate directly by eliminating angle theta that this distance should be equal to length times this number m times the wavelength divided by the distance between the two slits. Only when, should keep it in mind, only when theta is small, much, much less than 1 radian. So that works for several maxima close to the central one. First, second, third. Well, now let's just solve a problem, specific problem. This is a Young's double slit experiment with the red light travels through a device. So what do we know? Well, we know that eventually on the screen, away from the device, right in front of the device, we should observe central maximum, m equals 0. And then we should observe the first maximum, the second, on both sides. Oops, 1, 2. What are we looking for? So the wavelength is 664 nanometers, and again, nano means 10 to the negative 9. The slit separation or sources separation, D, is 0.00012 1.2 times 10 to the negative 4. (120) negative 6. That's how people would write it, micrometers, just in case. And the distance from the device to the screen is this. Calculate the distance on the screen from the central fringe to the third order. We need the third one. And we are looking for this distance. We call it normally L3. Just 2 minutes ago, we have derived the expression for the distance number m. using a combination of two equations. And the approximation. So all we have to do now is just use this expression for the third maximum times 3 times, well, okay, if we use meters, that's it. Please tell me your answer. Plus, I was pressing plus. One, two, three, four. Yes. I don't know. To make you to ask this question. Thank you. Because my number was way off. I was searching for the reason. Now we have the reason. Yeah, well, let's just write it correctly. I don't know. But I told you, well, not you, you didn't take PY105, right? With me. You did? So you know that our brain plays tricks on us. Good job, but don't do it anymore. Can't promise. So the wavelength over, what is it, 1.2 times 10 to the negative 4. Yeah, that's the answer. 2.75 times 3 times 664 negative 9 divided by 1.2 negative 4. Yeah, that's reasonable. 0.0456 meters, or close to about 5 centimeters. So that's the screen, and 2.75 meters is about, well, like the first row. So if we had a device there, light would travel on the screen. We would see red spots spaced by about 5 centimeters away from each other. Well, I guess that's a solution. Yep. And here, the solution actually doesn't use the approximation. So you don't have to technically. Yeah. This is how it also can be done, but it takes more time. First, you can calculate that angle number 3, and then you can use that angle to calculate the exact value, but you don't see a difference. It's exactly the same number. So that is why using approximations just saves time. Moving on. A next situation. The interference pattern generated by a wave traveling through a narrow slit. Not this one, this one. So when a wave travels through an opening, in this experiment, the wavelength is actually less than the size of this opening. And on the screen, we would see just one bright spot. And nothing here or there. The shadow would be formed. But if we make the opening, the size of it, close to the wavelength of a wave, in that case it starts bending, and after that it starts interfering with each other according to the Fresnel-Huygens principle. And here on the screen we should start observing the interference pattern, again bright and black spots, but of a different, slightly different shape. Again, in this situation, we can use a single source, like a laser pointer, and then do it to bending, do it to diffraction on the edges and interference. On the screen, we would see something like this. If we used the red laser, we would see a very bright, one single bright red spot right in the middle across the device. And then more wide, bright spots. And because they're wide, we cannot assign any specific location to that, which means we cannot actually call them maximum. We cannot count them as maxima, but they spaced by relatively narrow fringes with no light at all. So now, for this pattern, we should count only minima. And if we do that, to describe the location of a minimum, we have to use an angle, which is related to, well, what is involved? The wavelength, of course. For the red, it's red. For the green, it's green. For the blue, it's blue. Where else? Well, the location of the minimum. So first minimum, second minimum, third minimum. And of course, how wide the slit is, the width. We can make it very narrow. We can see a very good pattern. If we make it wider and wider and wider, the pattern eventually disappears. And of course, again, this is a gross exaggeration. We cannot see by naked eye the distance between the edges of this slit. It's impossible. So for us, it's just a device. Well, that's all we need to know about a diffraction pattern of a single slit when light travels through. Now we can solve a problem. Again, a red light travels through a single slit. You have to draw a picture. This is the slit. That's the screen. And we need to know how to draw a pattern because they are different. Again, this is the pattern for a double slit or double source. many consecutive bright and dark fringes. But for a single slit, the pattern looks differently. Right in the middle, we should have one bright, large spot. And then on the left and on the right, more. But we don't count them, we count minima. This is the minimum number one. This is the minimum number one on the right side. So what are we calculating? What are we looking for? This is what we need to calculate. How wide the central spot is. There is no special variable for that. Let's call it, I don't know. I don't want to use a W because W usually is set for the width of the slit. So I'm going to use, please pick a letter. Perfect. That's what we're looking for. So light travels, light travels to all directions, but, that's what I should say, but this black line represents the absence of light. And of course, we can draw the perpendicular to the screen. It hits the screen in the middle of the spot. This is theta 1. The equation which relates the mth minimum angle, wavelength, width is this. So we can use this equation for the first minimum, first. Now, again, this distance is 2 meters, but the slit is 30 micrometers wide, 30 times 10 to the negative 6. So we can expect that this angle theta 1 will be very small, much less than 1 radian. You can calculate it, of course. However, if we use this approximation, now we can use this angle to calculate a half of A. This is what we used to call L1, and this is 1/2 of what we're looking for. So 1/2 of A, which is L1, from this triangle, L1 theta 1, should be equal to the distance to the screen times tangent. However, as we know, for small angles, we can just drop the tangent symbol. Now, if we want to calculate this width, it's going to be 2 times length times angle in radians, which is wavelength over W, 2 times, don't make the same mistake again, 640 nanometers over 30 times 10 to the negative 6. Four times 640 nanometers divided by 30 micrometers, 0.085 meters, or about, well, 10 centimeters. That's good enough. This is how wide it should be. Well, and finally, what's going to happen if instead of one or two sources of slits, we have many, very, very many? A device like that has a name, diffraction grating, and to make it, we take a piece of glass and we start scratching it. Just the distance between two scratches should be tiny, fraction of a millimeter. So light doesn't go through scratches, get reflected, but it goes between. That's it. And now, so if we know how many lines, or people call cuts, are done, we know the length, we can calculate the distance between two adjacent openings, slits. This fraction tells us how many slits per millimeter is done. And now we can imagine what's going to happen if we're going to start covering some of those. So interference is happening here. The fact of the matter is that if we use a diffraction grating and a laser pointer, and we will, on the screen we will see only several narrow bright spots with a vast amount of no light at all. And again, because there is no light here, we cannot call it a minimum anymore. We cannot pinpoint the location of it, but we still can pinpoint the location of those bright fringes. So again, we observe a central maximum, then the first maximum on the left and first maximum on the right, second maximum on the left, second maximum on the right. And those locations should be described by equation which we already know for a double slit. So technically, for diffraction grating, we already know everything we need to know, but we cannot treat angles as small anymore. The distance from the central maximum to the first is larger, so this angle will be definitely greater than like 10 degrees. So for diffraction grating, we must use a sine or tangent or wherever it is. We cannot use approximations. So let's solve a problem. Again, angles are not small anymore. Typical problem. A light with a given wavelength, this is actually on the blue side, travels. So when I read it and I encounter a complicated word, I change it to a simple word. So incident, it's too difficult. So travels through a diffraction grating with 1,000 grooves, cuts, lines per millimeter. That's it. The screen is 2.75 meters away. Calculate everything, basically. So again, a device, a screen, the distance from the device to the screen, 2.75. On the screen we will see small bright spot right across the grating. First maximum, second maximum, and also on another side. We need to calculate this distance from first to second, L1, 2. Now, of course, geometry tells us immediately L12 is equal to the difference between distance from central to second and distance from second to first. That's geometry, not physics. For each maximum, we can write this equation. The condition for the maximum number m, oops, m, I said m, sine theta m what do we have to do? We have to use it twice. Have to calculate the angle number 1, which should be equal to, well, 1 times wavelength divided by the distance between two adjacent slits. Then we have to take inverse sine of it. And now we have to do this, the inverse sine of 2 times the wavelength divided by this. What is d? Again, d is the distance between two adjacent slits. So the diffraction grating looks like this. It's a long, I don't want to use L, yeah. L is here, so LG. And it has many cuts. So this is what D is. But what we know is the opposite. We know that's called density. We know that it's N over L. It is 1,000 slits per millimeter. That's what we know. So this tells us how to calculate D. D will be 1 over density. Just flip it over. So D will be 1 millimeter divided by 1,000, which makes it 10 to the negative 6th of a meter, 1 micrometer. So, and the wavelength is equal to 480 nanometers. And now we can calculate angle number 1, angle number 2. What do we do next? Well, next is geometry. For example, theta 1, yeah. Tangent of theta 1 is equal to L1 over L. Tangent of theta 2 equals L2 over L. Hence, L1 equals distance times tangent of the first angle. L2 equals distance times tangent of the second angle. And finally now, we just calculate the difference, actual mathematical difference. We cannot use approximations. I'm not going to do this calculation now. I want to answer, well, actually I have it here. And I want to answer the second question. Tomorrow. All right, thank you very much. Just remember that the maximum angle can be reached is 90 degrees. It cannot go above 90. For every pattern, there is a final maximum at the 90 degrees. I will solve it tomorrow, but now you can solve many homework problems. Many homework problems.